Welcome back. This is the next section, quantitative aspects of chemical change, and it involves calculating amounts or quantities of chemicals. And the unit is 1 on page 171 to 225. First of all, we'll do some revision. So this is lesson 1. We're going to look at the atomic structure, mass, and mole. Now, Antoine Lavoisier was the first man to start doing quantitative chemistry. So that is why he is called the father of modern chemistry. Before that, people just mixed things and at random together to try and make gold. Firstly, I want to look at the concept of isotopes. They are atoms of the same element with the different numbers of neutrons in their nucleus. That is why the mass numbers would differ. So the relative mass numbers on the periodic table are not integer values, they are decimal values. So let's look at the meaning of isotopes. Isotopes mean that you've got chlorine atoms. This is chlorine 35. So the mass number is 35, but the atomic number is 17. This one, chlorine 37, the mass number is 37, and the atomic number is 17. So the meaning is there will be 17 protons in the nucleus, 17 electrons around the nucleus, and 35 minus 17 will give you the number of neutrons, 18 neutrons in the atom. We do the same for chlorine 37, 17 protons, 17 electrons in the neutral atom, and there would be 20 neutrons. So the mass of the atom differs because of the number of neutrons. Next we get the relative atomic mass as a definition. It is the average mass between the isotopes of the element compared to the mass of 1/12 of the mass of carbon-12. So 1/12 is 1. 1/12 of 12 is 1. 1 times 1 will give you the mass of hydrogen, which is 1. 16 times 1 will give you the mass of oxygen's isotope. Let's go through some examples we know already, calculating relative masses. First of all, we've got chlorine 35. 75% of chlorine is chlorine 35. So to calculate the relative mass of chlorine, you take the mass number of the isotope and you multiply it by the percentage as a decimal. And you add to that the mass number of 37 times 25% as a decimal, and that gives us an answer of 35.5. And these are atomic mass units. Next, we get magnesium. There are 3 common isotopes, magnesium 24, 25, and 26. So the relative mass of magnesium is calculated by taking the mass number 24 and multiplying it by 80%, 0.8, plus the mass number of 25 times 10%, plus the mass number of 26 times 10%. And that gives us an average mass, the relative mass of plus 25, 2.50 plus 2.6, 24.3. Now these values, the percentages as well, the percentages are rounded values. That's why you won't find them, the answers to be exactly like those on the periodic table. We also only considered the most common isotopes of the elements. Next, we're going to look at relative molecular or relative formula mass. Now, the molecular mass is calculated for molecules which are covalent compounds, where the formula mass are for ionic compounds. So these are covalently bonded, and so they're nonmetals, and these are ionic. Ionic bonds between the atoms. So let's look at some molecular mass. I'm going to do one example. Commonly, carbon dioxide's formula is that. So the molecular mass would be 12 plus 2 times 16, and that, I guess, gives us 44 atomic mass units. For copper chloride, copper 2 chloride, the formula mass would be 65.5, or is it? Is it? Sorry, it's 63.5 plus 2 times 35.5. So it's 71 plus 63.5, which makes it, the formula mass is 134.5 atomic mass units. Next, we get to the concept of the mole. It is the measure of the amount of substance. We use a little n to symbolize the mole, and the unit is written as mol. 1 mole of any substance will contain the same number of particles as the number of atoms in 12 grams of carbon 12. Carbon is taken as the most common element. And we know that the number of particles is 6.022 times 10 to the 23 particles. We'll discuss that a little bit later. So this brings us to the mass of a mole, molar mass. It is the mass of 1 mole of a substance. So let's do some examples where we compare relative mass to molar mass. We did the relative mass for carbon dioxide earlier, which was 44 atomic mass units. That's for 1 molecule. Now, the molar mass of carbon dioxide would be the mass of 6,022 times 10 to the 23 molecules, and that would be 44 grams per mole. The next example, copper chloride, we had the relative mass is 134.5 atomic mass units. That is for 1 unit. Okay, now the molar mass for that would be 134.5 grams. Okay, per mole. Easy. Right, the last slide in this, the mole and balanced chemical equations, we say stoichiometric ratios. So my example is the reaction that makes clear lime water milky between calcium hydroxide and carbon dioxide. The mole ratio is the stoichiometric ratio given by the balanced equation. So 1 mole of calcium hydroxide will react with 1 mole of carbon dioxide to give 1 mole of calcium carbonate and 1 mole of water. So, what is the mass ratio here? I know that the mass ratio is 44 grams for carbon dioxide, and I know it is 18 grams for water. Calcium carbonate, I think, is 100 grams. So it's 40 for calcium plus 12 plus 3 times 16. That is 100 grams. Okay, so for calcium hydroxide, it's 40 plus 2 times 17, which is 74 grams. Let's just double check on ourselves. There is something like the conservation of mass. Because matter can't be created or destroyed, so I'm going to double check myself. 74 plus 44 gives us 118 grams. And on the other side, the products is also 118 grams. But what we are going to work with is the mole ratio. It's a much simpler ratio than the mass ratio. So I hope you enjoyed this revision session. Next we will look at some constants.